Okay, so now for the reciprocal functions, secant and cosecant. So let's start with cosecant. So cosecant, let me write that better, cosecant x is the reciprocal of sine, right? So cosecant x is the same as 1 over sine x. So think about what we've talked about with respect to rational functions. I can't divide by 0. So sine x can't be 0. That is where cosecant x will be undefined. And in fact, that will be where we have vertical asymptotes, wherever sine x is equal to 0. Okay, so we can use that to help us graph the cosecant function. So the easiest thing to do is just to graph y equals sine x, and then you can build the cosecant function from there. So let's start with just regular old y equals sine x. So let's take our pi over 2, pi, 3 pi over 2, and 2 pi. So notice we can keep going again forever, right? And notice the pattern here. This is pi over 2. Pi you can think of as 2 pi over 2, 3 pi over 2. 2 pi would be the same as 4 pi over 2. So if I want to continue that pattern, the next one would be 5 pi over 2. The next one would be 6 pi over 2, or 3 pi. Again, we can do the same thing in the other direction. All right, we know sine goes as high as 1 and down to -1. All right, so I know that sine of 0 is 0, so the pattern will start here at the origin. And then we go up to 1, back to middle, down to -1, back to middle, up to 1, back to middle, and again that continues. So sine, I'm just going to kind of use a dotted line, looks like this. Again, we know that pattern will go on and on. So just like we said, okay, cosecant is undefined whenever sine x is equal to 0. So when is sine x equal to 0? Well, that would be at the x-intercepts. So sine x is equal to 0 here, at pi, at 2 pi, at 3 pi. So that's where my vertical asymptotes are for cosecant. So I will have a vertical asymptote here, and here, and here. So now the point or points that sine and cosecant share are at those other values, at pi over 2. So cosecant of pi over 2 is also 1. Cosecant of 3 pi over 2 is -1. Cosecant of 5 pi over 2 is 1. And then the way the cosecant function falls in is, again, it's the reciprocal function. It looks like this. And that's the pattern that continues forever. So domain, all right, we have to exclude, right? X equals 0, x equals pi, x equals 2 pi. Very similar to when we came up with a domain for cotangent, right? So x can be any real number, but it can't be any integer multiple of pi. So I can say k times pi, where k is an integer. Now the range is, so the sine function really isn't here. The cosecant graph is just the solid line. So there's nothing in between -1 and 1. So the range would be from -infinity to -1, meaning down here, or from 1 to infinity. Okay, and cosecant is going to work really similarly. So for cosecant, let's move this up a little. For cosecant, or for secant, excuse me, we're going to base this on the graph of cosine, right? So cosecant, I keep saying cosecant, secant, oops, sorry about that, secant x is equal to 1 over cosine x. So that means that secant x will be undefined when cosine is equal to 0. So I can use this information again when I'm coming up with the graph. All right, so we've got pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and again, we can keep going in both directions. As high as 1, as low as -1. I know at 0, cosine is 1, and then we know the pattern from there. Right, so the cosine graph, I just kind of use a dotted line. Will look like that. And I will have asymptotes at those intercepts because that's when cosine is equal to 0. So I'll have a vertical asymptote here at pi over 2, at 3 pi over 2, and at 5 pi over 2. And the secant graph will fill in just like cosecant above. We'll have a cup here, down here, up here, and that's the pattern that continues. So the domain will be similar to that of y equals tangent because we're excluding x values like pi over 2, 3 pi over 2, 5 pi over 2. So again, x can be any real number, except x can't be, we'll say pi over 2 plus k pi, where k is an integer. And the range will be exactly the same as cosecant, from -infinity to -1, or 1 to infinity.